Hello everyone, welcome back to the e-Shikshana online course on heat transfer. I am Karthik. I am working as an assistant professor in the Department of Mechanical Engineering, B&M Institute of Technology, Bengaluru. As you are already aware, so the e-Shikshana course on heat transfer is going on, and the first two modules of the prescribed syllabus have already been covered by Dr. A.M. Nagaraj. So now I will be exclusively covering the module 3 of the syllabus, so which is convective heat transfer. Before we begin with the lecture session, so I would like to extend my gratitude to Dr. A.M. Nagaraj and VTU for providing me with this unique opportunity. With that said, so let us jump into the module 3, which is convective heat transfer. So before I begin with the lecture session, so I'd like to apologize for the audio quality and also request you to disregard any disturbances and cooperate with me. Now, the syllabus that is prescribed for module 3 will deal with forced convective heat transfer and also natural convection heat transfer. Now, the scope of the syllabus and the depth to which we can deal with it is somewhat compromised by the time, by the availability of time. So sometimes some concepts, so I'll be providing you the suitable reference material, or I'll be guiding you to a reference which you can refer to, and you can come back to me if you have any doubts or if you require any clarifications. So the reference material or the reference books that I will be referring to this module for this module will be, one is by Professor S.P. Sukatme, so which is a textbook on heat transfer, which is published by Universities Press. The other one is by Professor S.K. Som, Introduction to Heat Transfer, so which is published by PHI Learning Private Limited. So both these books have very good information and an in-depth coverage of convective heat transfer, which you can refer to for a good fundamental understanding of the topic. Okay, now let us begin with lecture 1 of the series. So I'll be trying to cover the entire module in probably 10 lecture sessions. So we'll try to deal with the maximum syllabus that is possible in this duration. Let us utilize the available time to the best extent possible. The first lecture, I'll present you an outline of today's lecture session. So I will begin with a very brief introduction to convective heat transfer. After that, we will take up forced convective heat transfer, and I'll present a dimensional analysis of a forced convection problem, and we will derive some non-dimensional constants, and we'll discuss the physical significance of these non-dimensional numbers, which are very vital to forced convective heat transfer or convective heat transfer in general. After that, if time permits, so we will try to derive the differential equation of mass conservation or differential continuity equation in Cartesian coordinate system. So this will be the outline of today's lecture. and we'll try to cover as much of this as possible. Okay, so let us begin with a very brief introduction to convective heat transfer. So you are already familiar with convective heat transfer in the introduction of module 1 itself. So you know that there are three modes of heat transfer: conduction, convection and radiation. And conduction is a predominantly a molecular phenomenon, so which relies on diffusion of energy at a molecular level. So convective heat transfer can be simply, it is just conduction which is assisted by advection of a fluid. So here you will have a solid surface invariably upon which there is a fluid which will be moving. Now you have to recognize that the movement of the fluid is a bulk movement. So which means there is a macroscopic movement of molecules due to the temperature gradient which is prevailing. And the movement of this fluid can be due to an external agent like a pump. So if that is the case, we refer to the situation as forced convective heat transfer, or the fluid's movement may be due to density changes or buoyancy. Then you refer it to as free convection. So in either of these heat transfers, so you have to recognize that there is a solid surface upon which there will be a fluid which will be moving. Now the heat transfer rate during convective heat transfer is governed by Newton's law of cooling, which you are already familiar with. So it is given by H A into Ts minus T infinity. So Ts is the surface temperature in this case. So we are assuming that the surface is at a higher temperature than the fluid, but the vice versa is also true. Now, in any convective heat transfer problem, so the motive for solving such problem is to estimate the value of heat transfer coefficient. So one will be interested to know what is the value of this heat transfer coefficient. As you can clearly see from the Newton's law, the value of heat transfer coefficient dictates the heat transfer rate. So higher the heat transfer coefficient, you will have higher heat transfer rates also by convection. Okay, now to physically appreciate some of the parameters of this problem, so let us consider an external flow problem. So now what I mean by an external flow problem is this. So let me consider a plate. This is a solid wall. Let the temperature of the wall be Tw. So there is some fluid which is moving, it is flowing above the plate. So let its temperature be T infinity. So let us assume that Tw is greater than T infinity. So we assume that the wall is at a higher temperature. Now, so obviously there is heat transfer in this direction. So this is Q. So heat is transferred from the solid wall to the fluid. Now according to Fourier's law, so the heat conducted from the wall surface to the fluid is given by Ka. Here A is the surface area into the gradient of temperature. So the suffix F stands for fluid. So thermal conductivity of the fluid, surface area of the fluid, and to the gradient. So let us assume that this is X and the vertical coordinate is y. Okay, so the gradient in the y direction, which is dt by dy, so at the wall, so this should be equal to HA Tw minus T infinity, so which is the heat convected. So since a surface cannot retain any heat, so this equality should always hold good. Now if I express the temperatures in the form of a non-dimensional temperature, so this is the non-dimensional temperature theta, so which is given by temperature at any point minus T infinity divided by wall temperature minus T infinity, and also let us non-dimensionalize the length in the y direction, which is y by L. So if we substitute it, so you will obtain a ratio. So this is a non-dimensional ratio, obviously. So this ratio is referred to as the Nusselt number, so which is named after a researcher. Nusselt number is a very important parameter in convective heat transfer in general. Here you have to observe that the Nusselt number so appears similar to Biot number. So you have already come across Biot number in the transient heat conduction, so which is also given by HL by K. But the difference here you have to recognize is that the conductivity there in the Biot number is that of the solid, but here it is of the fluid. So please be careful. So Biot number is nowhere related to Nusselt number, even though it appears the same. So Biot number is with respect to conduction and Nusselt number is with respect to convection. So there you have to take the conductivity of the solid material. Here we are concerned about conductivity of the fluid. So you please note this difference. Okay, let us continue. So now, as you saw, the Nusselt number, so which is the non-dimensional temperature distribution, is actually a function of fluid properties. So it is a function of density of the fluid, viscosity of the fluid, the free stream velocity u infinity, the length of the plate, conductivity of the fluid, and specific heat of the fluid. So you can recognize that here in this function the variables density, viscosity and velocity are related to fluid properties. So which means that fluid properties influence the heat transfer rate. So how are they influencing heat transfer rate? Because they change the value of heat transfer coefficient, which in turn brings about a change in heat transfer rate due to convection. So since these are fluid properties and they are associated with fluid flow, it is important that we review the principles of fluid mechanics. So fluid mechanics becomes very important in the analysis of convective heat transfer. So here what we will do is we will take up the conservation of mass and momentum, which are related to fluid flow, and we will couple it with conservation of energy, so which will give us the solution to our forced convective heat transfer problem. So conservation of mass and momentum will actually give you the velocity profile and also the drag force, skin friction coefficient for a flow problem. And when we couple it with the energy equation, we will get the temperature distribution, and through the temperature distribution we can also obtain the heat transfer coefficient, the value of heat transfer coefficient. So this is our motive. So why we should study fluid mechanics is because the heat transfer coefficient depends on the fluid properties, and it's a function of fluid properties, that is changing or varying any fluid property will result in a variation of heat transfer coefficient. So with this, let us move on to forced convective heat transfer, and let us take up the dimensional analysis of a typical forced convection problem. So by doing the dimensional analysis, we will try to get different dimensionless groups. So, and we will also explain the physical significance of these groups pertaining to convective heat transfer. Okay, so already we had in the previous slide listed out the fluid properties which will influence a heat convective heat transfer problem. So let us, you can find the list here. So the parameters of interest are convective characteristic length. So this characteristic length L can be the length in an external flow problem, length of the plate. So if you take an external flow problem, so this can be the length of the plate, or if you take flow inside a pipe, so it can be the diameter of the pipe. So depending on the problem, so which can be either an internal flow problem or an external flow problem, so you can have the characteristic length changing. Next is fluid density, rho, the velocity of flow, which is v, so you can also take it as u, so it doesn't matter. Fluid viscosity, mu, the dynamic viscosity, that is. Specific heat of the fluid, Cp, thermal conductivity of the fluid, K, and heat transfer coefficient itself. So these are the parameters which influence the physical phenomenon of forced convection. So I have also listed out the dimensional equivalents for these parameters. So you can see here. So you have to convert it into MLT and T. So here both time and temperature are present. So please be careful and note it. So now the characteristic, the function, we can write it as H is a function of rho, mu, V, L, K and Cp. Now you are familiar with the pi theorem, Buckingham's pi theorem in your fluid mechanics course. So we will be utilizing that. So if you can see, the number of independent variables are 7. Okay, and the number of fundamental variables are 4: mass, length, time and temperature. So therefore the number of independent dimensionless groups will be 7 minus 4, which will be 3. Okay, so now we have to select some repeating variables. So to select these repeating variables, so you know that one should be a kinematic property, one should be a dynamic property. So if you have temperature, one property should be related to temperature and one should be a geometric property. So let us select those. So conductivity will be related to temperature. Density is a dynamic, is a kinematic one. L, characteristic length, is a geometric property. Mu is a dynamic property. So we are selecting these 4 as repeating variables. So if you select these as repeating variables, you know how to express the dimensionless groups and solve for the powers. So we will get these 3 dimensionless groups. The first one, so you are already familiar with this in your fluid mechanics course, rho VL by mu, which is the Reynolds number. The second non-dimensional number, mu into Cp by K, is called Prandtl number. And the last one, HL by K, which is the Nusselt number. We have already come across this at the start of today's lecture. So you know that according to pi theorem, you can express the dimensionless groups as functions of other dimensionless groups. So which leads us to a conclusion that Nusselt number is a function of Reynolds number and Prandtl number. And usually it is a power law function. So it will be in the form of Nusselt number is equal to some constant into Reynolds number to the power of m. Prandtl number to the power of n, where m and n and constant c will depend on the flow situation. Okay. So now a doubt may arise that what happens if we select different repeating variables. So the result will still be the same, but you may not get those dimensionless constants directly. So you may have to do some manipulation, and finally you will again obtain the same dimensionless groups. So it is better to select the repeating variables that we took so that we will end up with the constants in the first step itself. So please note that this is an important question for your examination also. Now let us quickly move on to the physical significance of these dimensionless groups, which are very, very important to recognize and to appreciate. So let us first take the Reynolds number. So what is Reynolds number actually? So it is the ratio of the inertia force of the fluid to the viscous force that is acting on the fluid. So you know viscous force is due to the shear stress. So if you have a surface and a fluid is moving on it, so you are familiar with the no slip boundary condition. The fluid that is adjacent to the wall will have zero velocity. So which exerts a resistance to the layers of the fluid above it. So which will result in a propagation of momentum disturbance in the y direction. We took that external flow problem, so we can take a similar example here. So what I mean to say is, so if you have a solid surface like this and a fluid is moving on it, so due to the no slip boundary condition at the wall, so you will have your velocity varying like this. So that is the velocity which is at the wall. So here the velocity u is 0 because of no slip boundary condition, and this is the viscous force which will be acting on your fluid. And you know from Newton's law, so the uh, shear stress is proportional to the velocity gradient. So we are considering the same. So that is for a Newtonian fluid. So we are considering the same here in the next step. So here, okay, so which will yield the final form of Reynolds number, which is rho LV by mu. So what does this actually represent? So Reynolds number actually represents the relative magnitude of inertial and viscous forces which are acting on the fluid. So a very high value of Reynolds number indicates that the inertia force dominates the viscous force, and a lower value of Reynolds number indicates that the viscous forces are predominant over the inertial forces. So you know that you can decide the type of flow, whether it is laminar or turbulent, by the value of Reynolds number. For an internal flow situation, you know that for a pipe flow, Reynolds numbers of greater than 2300, we regard them as turbulent flows, and if it is less than 2300, we call the flow as laminar flow. So in laminar flow, the diffusion of momentum is due to viscosity only. So it is augmented by macroscopic mixing during turbulent flow. The turbulent flow, the characteristic of turbulent flow itself is a macroscopic mixing, so which is not visible in a laminar flow. Here the flow, in laminar flow, you will have a layered type of flow, which you have already come across in fluid mechanics. For a given fluid, so Reynolds number increases when velocity of flow increases. So again, we are establishing a relationship between fluid properties and convective heat transfer. So when there is a very high value of V, obviously you have a very high value of Reynolds number. And when you observe that external plate flow problem, so if you increase the velocity, so new fresh fluid will come into contact with the surface, and the dissipation of heat due to convection will be increased. So a high velocity of flow will lead to an improved dissipation of heat or convective heat transfer. So a high value of Reynolds number indirectly is giving you an impression that heat transfer rate or heat dissipation rate is high. So we can conclude that high Reynolds numbers will indicate that the dissipation of heat due to convection or advection of the fluid is very high. Okay. So the next non-dimensional number of interest is the Prandtl number, which is a very important parameter in convective heat transfer. So actually, when you look at those fluid properties which we had considered earlier, the dynamic viscosity and density can be actually coupled together to get kinematic viscosity. So it is actually kinematic viscosity, so which is more meaningful than those two separate. So what is kinematic viscosity? So it is the relative ability of the fluid to transfer momentum change. So with respect to its ability to sustain momentum. So if you see the ratio mu by rho, so mu actually viscosity actually conveys to you as to how the momentum disturbance at the wall is being transferred to the layers above the wall. Okay. And what is density actually? Density is something, it's related to inertia. So it is something which is trying to sustain the momentum. So it is not allowing the fluid to slow. Whereas viscosity is acting as if it's a resistance to flow. So a relative or a relation between these two parameters is established using kinematic viscosity. So it can be proven and derived that the kinematic viscosity is related to velocity boundary layer thickness, so which is given by delta. So again, the boundary layer theory was introduced to you in the fluid mechanics course itself. So now if you find an analogous property with respect to heat transfer which is similar to kinematic viscosity, so you will find thermal diffusivity, so which is given by K by rho Cp. So in this case we will calculate this for the fluid, K by rho Cp. So this actually indicates or represents the relative ability of the fluid to conduct heat with respect to the ability of the fluid to store thermal energy. So it is somewhat very similar to the kinematic viscosity definition. Conduction of heat with respect to thermal inertia or thermal storage. So we can um, put it in those terms. Now a ratio of these two is actually your Prandtl number. Also, it is observed, it can be observed that the thermal diffusivity is related to the thickness of thermal boundary layer. So you will have a velocity boundary layer and also a thermal boundary layer. So thermal diffusivity is related to thermal boundary layer thickness, and kinematic viscosity is related to velocity boundary layer thickness. So now Prandtl number is the ratio of these two parameters. So indirectly it is the ratio, or it is related to the ratio of the velocity boundary layer thickness to thermal boundary layer thickness. It's very important to recognize this ratio. It's the measure of relative effectiveness of momentum and energy transport in the medium by diffusion. So this is the actual definition of Prandtl number. So let us look into three typical cases where this Prandtl number the value of the Prandtl number actually gives you some physical significance. So let us take up case 1. So for viscous fluids in the sense like oils, so here it is observed that the velocity boundary layer is thicker compared to the thermal boundary layer. So it's also important to appreciate the magnitude of these values. When I say velocity boundary layer, so it's just in the order of a millimeter from the surface. Even thermal boundary layer is also of the same order. So here the momentum disturbances travel through the fluid more rapidly compared to the temperature change. So for these oils, that is for viscous fluids, Prandtl number is found to be greater than 1. Now for gases especially, so the development of the thermal boundary layer and the velocity boundary layer is almost at the same rate. So we will find that their thicknesses are almost comparable, and in this case the rate of momentum transport is comparable to heat transfer by conduction, so which will make the Prandtl number very close to 1. For air in particular, the value is in the order of 0.7. Another extreme that we see is in liquid metals, where the thermal boundary layer develops very quickly or rapidly compared to the velocity boundary layer, owing to the metallic nature, wherein conduction is very quick compared to other fluids, compared to other elements. So here the Prandtl number is very less than 1, and this is due to very high thermal conductivity of metals. So please note these three cases of Prandtl number greater than 1, very close to 1, and which is less than 1. So which will be useful for our analysis of different forced convection cases later. Now coming to Nusselt number, the third non-dimensional number, so which was already discussed. So it represents the non-dimensional temperature gradient. So it can be rearranged in the following format. So I have just sent the characteristic length to the denominator and also divided both numerator and denominator by the temperature difference delta T. So you know that the numerator is proportional to the convective heat flux and the denominator to the conductive heat flux. So what your Nusselt number is indicating is the enhancement of heat transfer that is brought about by convection. So a very high value of Nusselt number will indicate that convection is happening at a very high rate and your heat dissipation due to convection is very high. So a lower value will indicate that the convective heat transfer is not happening at a very high rate. So this is what Nusselt number's importance is. There are other non-dimensional numbers also, which can be derived by rearranging the three fundamental numbers that we have already discussed. So one is called Prandtl number, so which is specified only for forced convective heat transfer. So it is given by Nusselt number by Reynolds into Prandtl number, and it's actually very convenient to use Prandtl number in forced convective heat transfer in some cases rather than using Nusselt number only. Again, you have another number which is again used in forced convection, which is called Prandtl number, which is a product of Reynolds and Prandtl number. Okay, so this ends our discussion on the dimensional analysis of typical forced convective heat transfer problem. Now we can proceed to a review of principles of fluid flow, so which involves our discussion on a law of conservation of mass, momentum, and energy. So we will be trying to derive differential equations for mass conservation, momentum conservation, and energy conservation. So this flow diagram actually gives you a brief idea of our entire discussion that will be ensuing from now onwards. So we will, as you can see, the fundamental or governing laws are conservation of mass and conservation of momentum for fluid flow. So which will result in a differential continuity equation and the Navier-Stokes equations. So what you will get from these two equations when you solve them is that you will obtain a velocity distribution, pressure drop if it is an internal flow problem, or drag force if it is an external flow problem. Then when we couple this velocity distribution with conservation of energy, you will obtain the final temperature distribution and the heat transfer coefficient, which is the solution for our forced convective heat transfer problem that we are trying to solve. So what is the framework? So we will start with conservation of mass and momentum for a fluid flow situation, which will result in the velocity distribution, pressure drop, and drag force, calculation of drag force. So this velocity distribution, when coupled with the energy equation, differential energy equation, will result in the temperature distribution for the convection problem. So and also which can be utilized to solve the forced convection heat problem and get the value of heat transfer coefficient. So this is the entire framework of our discussion. Okay. So now let us begin with the conservation of mass. So which is, let us derive the differential equation of continuity. So to do that, let us consider a control volume, so which is as shown in the figure. So you can look into that control volume. So the volume of the differential element is dx, dy, dz. So now the rate of mass that is entering the control volume along the x direction is given by rho u dy dz. Okay, so the rate of mass that is leaving the control volume is given by a Taylor series expansion. Here we are not considering density as constant, so density will also change and also velocity will also change. So this is from Taylor series expansion and neglecting higher order terms. So what we have done here is we have just written the continuity equation, which is rho AV. So rho density, area in the x direction, so that is this area. So this area is dy into dz. So it will become rho times u velocity into area, which is dy dz. Similarly, after it passes through a distance of dx, so by using Taylor series expansion, you can just write, sorry, here I have missed a dx into dy dz. So I have also shown the same expression in the y direction. So the velocity in the x direction is u, in the y direction is v, and in the z direction it's w. So I have shown the same expansion in the y direction also. Please, you can write the same expressions in the z direction also. So in order to prevent the things from becoming very clumsy, so I have just shown only two dimensions, two characteristic dimensions. So now let us consider the net rate of mass efflux from the control volume along the x direction. So it is rate of mass leaving the control volume minus rate of mass entering the control volume. So if you neglect the higher order terms, that is the product of two partial differentials, so which will obviously be very less. So you will end up with this equation. So you will end up with this. Okay. So which is nothing but, so you know that differential of u into v is u into differential of v plus v into differential of u. We just utilized that and we have clubbed the expression. So now you can write similar expressions along y and z directions also. So now there will also be some rate of mass which gets accumulated within the control volume, which can be written in very simple terms as the as rho into volume, which is mass. So this is mass, the change of mass with respect to time. So which is nothing but dx dy dz into d rho by dt. So now for conservation of mass, you know that the net rate of mass efflux from the control volume plus rate of mass accumulation should be 0. There should be no mass which should be accumulated within the control volume. So if you do that, so you will end up with this equation, so which is the differential equation of mass conservation or continuity in Cartesian coordinate system. So in the vectoral notation, so it will become like this. Okay, where v is the velocity vector. V is the velocity vector. Okay. Yes. So now what are the assumptions that were made to solve the previous thing is that we assume that it is a stationary control volume and it's a non-deformable control volume. So these are the two assumptions that we have made to solve the to derive the previous equation. And now we can also derive the differential equation of mass conservation in cylindrical or polar coordinates also. So I have not derived it, so you can get the derivation in the book by Professor S.K. Song. So the detailed derivation is provided in that book. So I urge you to refer to that book in case you require the proof for this equation. So this is the differential equation for cylindrical or polar coordinates for mass conservation. Now, expanding the differential continuity equation, so which was the equation which is present here. So you have partial differential of rho into u by dou x. So I will just expand it as rho into dou u by dou x. So which is done in this slide. So you consider linear deformation of the fluid along the x direction. If you consider the linear deformation along the x direction, you will see that the linear strain rate is given by dou u by dou x. Similarly, you can write the expressions in y and z directions also. So now if you consider volumetric strain rate, so as demonstrated on this slide, so which is given by the final volume minus initial volume divided by the initial volume into change in time. So you obtain, or you see that you get it as dou u by dou x, dou v by dou y, and dou w by dou z. So which is the summation of linear strain rates. Now for a incompressible flow situation, the volumetric strain rate is 0. So that is, the summation of these three partial differentials will be 0. And please note that an incompressible fluid is different from incompressible flow. So what is an incompressible fluid? an incompressible fluid is the one where density is not a strong function of pressure. So that is an incompressible fluid. And what is incompressible flow? Incompressible flow is where volumetric strain rate is zero. So it's a kinematic assumption. Which one? The incompressible flow assumption, which is very different from an incompressible fluid assumption. So now for an incompressible flow situation, so you know that the volumetric strain rate is zero. So now in your equation, when you substitute it, so you will also get dou t, dou rho by dou t is equal to 0. So this left hand side, this thing, so according to your kinematics of fluid flow, so which you have already studied in fluid mechanics, is nothing but the material derivative or the substantial derivative, which is represented by capital D rho by dt. So this will also become equal to 0. So for an incompressible flow situation, so these two will be satisfied. So uh, for an incompressible fluid though, since density is constant, so the above equation, that is this one, is trivially satisfied. So it is already satisfied if your fluid is an incompressible fluid. So this concludes our discussion on differential equation of continuity or differential equation of mass conservation. So let us end our lecture for today. So in the next lecture, we will take up conservation of momentum and we'll try to derive the Navier-Stokes equations. Thank you.